Hi, good afternoon, everybody. My name is Chris Kelson. I'm senior geologist here at Atlantic Testing Laboratories. My job here at ATL is to do and handle anything and everything related to geology and rocks and minerals, so on and so forth. I also do a lot of work with concrete and concrete petrographic analysis, etc. Anyway, today's webinar is my attempt at sharing with the engineering world, the engineering folks, the geology behind why we see a lot of the hazards that we see. So this is part one of two parts of webinars entitled Geologic Hazards, Geology for Engineers. As Howard mentioned, just a few housekeeping rules. Again, feel free to send questions or comments to him directly via the chat button, and then we can address those questions and comments at the very end. And then, of course, throughout the course of the webinar, you will be presented with several really challenging and difficult questions, which need to be answered, of course, to get Pi credit for this webinar. Also, before I forget, because I can't show features and things on our slide with a laser pointer, I'll just use my mouse cursor, so please watch for that. All right, let's start off with a quick definition of what a geologic hazard is. It's any earth material, geologic event, or geologic process that is hazardous or potentially hazardous to life or property. So as far as earth materials go, we're discussing soils, water, minerals, rocks, etc. Geologic events would include things like landslides, right? Avalanches, mass movement of earth materials, earthquakes, volcanic eruptions, etc. And geologic processes would include the weathering of rocks and minerals, the erosion of rocks and minerals, the formation of karst, etc. So during the course of this presentation, we'll pick a few of those individual topics and discuss them in turn. The message I'd like everybody to take home today from the webinar is that it's definitely best to identify and mitigate hazards before they actually cause damage, right? So identification and mitigation is preferred versus reacting to something and try to remediate and repair it after it's already happened. So in this presentation, we're going to cover 5 specific topics: shrink swell soils, toxic soils, seismic activity, in particular faults and liquefaction, karst and the formation of karst topography, and then just rocks in general.
Chris, can you explain what karst is, please?
Sure. So karst is a type of topography that's formed when rocks are essentially dissolved by water. And give me a couple minutes to get further on into the presentation, and we'll cover it a little more in depth. But it's basically a type of topography formed by the dissolution of rocks. Good question. Okay, so let's start off our discussion discussing shrink and swell soils. These are soils that either volumetrically decrease or increase due to one of several factors that can include water loss or water absorption, mineral oxidation, temperature changes, etc. The end result of any of those things is that the soil settles differentially. It may heave and also therefore cause foundation damage. In this webinar, we're just going to discuss shrink swell soils in the sense that they experience volume increase or decrease due to water loss or absorption, okay? And the soils that do that or behave that way contain certain clay minerals that are the culprits to making that occur. So the example we're specifically going to talk about is a clay mineral called montmorillonite, and you may have heard of that mineral before. Montmorillonite is the major. Montmorillonite and bentonite are essentially the same, Okay, kind of the same idea, same mineral. The mineral montmorillonite is a phyllosilicate. Phylo meaning sheet, and it's a silicate mineral if you look at the formula, right? So it belongs into the mica family of minerals, and in particular it's part of the smectite mineral group. Here is the formula for montmorillonite, and I'm not really interested that you pay attention to most of that, except for the very end of that formula. You can see there's water in the mineral formula. The addition or removal of water in montmorillonite is what causes the mineral to expand or contract. The stick and ball diagram that I'm showing here is what montmorillonite looks like on the atomic level. It's a clay mineral that's comprised of TOT, or tetrahedral and octahedral sheets of atoms that are sandwiched together, and in between these TOT layers we can have cations and also water molecules that can get in there. So when water is introduced to montmorillonite and water can get in between those TOT layers, the mineral itself can expand, and depending on how much montmorillonite there is in the soil can expand anywhere from around 22% to almost 50% just by the absorption of all that water. The resulting pressure caused by the expansion of the montmorillonite in the soil can range anywhere from just a little over 1 atmosphere to almost 6.5 times atmospheric pressure. This is a picture of what shrink swell soils can do to a building foundation. Here in the grass, under the grass, we have shrink swell clays inside the soil, and their expansion and contraction are actually pushing in the side of that building's foundation. You can see the cracks in the concrete. Inside that same building, this gentleman is showing what straight up and down is using the plumb bob, but you can see where the wall is relative to straight up and down vertical. So clearly the walls are being pushed and affected by the shrink swell soil. So how to identify your soil as being as containing a mineral that may be prone to shrink and swell? Well, you can do one of two things. You can consult maps, either large-scale maps such as this one, which is of the entire country, and basically it's color-coded based on where certain shrink swell soils occur. Maps on a statewide scale or county-wide scale may exist. Here's an example of Texas, where basically everything's color-coded. Blue is low potential for shrink swell, and red is a high potential or frequency for shrink swell soil. So this would help identify an area if you're building in an area if it has this in the soil. Or you can actually get a sample of the soil and analyze it to see if montmorillonite, for example, is in the soil itself. So one way to do this is to collect a sample of soil and analyze it via X-ray diffraction, or XRD. And for those of you who are unfamiliar with XRD, it's an analysis that doesn't tell you what the sample is made of. It doesn't tell you elemental composition, but it identifies mineral constituents based on their atomic structure. So it gives you basically a fingerprint of which minerals are home in a particular sample. The relative height of the peaks are correlative to how much of a particular mineral is in the sample. Okay, but again, it's not a very quantitative thing. It's more like a qualitative example. Anyway, so this particular example shows characteristic fingerprint peaks for quartz, also calcite, some feldspars, but the M represents montmorillonite. And so if montmorillonite was present in your sample, you know what its fingerprint looks like on these peak patterns. You can identify it that way, and that's something I regularly tackle. But that's one way to identify if you're building in a place that may be susceptible to that. All right, so question number 1, please.
All right, Chris, go ahead.
Okay, thanks. All right, so question number 1, which of the following is not a process that could cause soils to shrink or swell? The answer would be C. Dispersion of carbon has nothing to do with it. Water gain, water loss, and mineral oxidation are all players in that game. All right, let's switch gears a little bit and talk about soils that are toxic. These are soils that contain or produce one or more elements that are dangerous to health. And I think it's important to understand that the presence or absence of any toxic elements in the soil is strictly dependent on the constituent minerals in the rocks from which the soil is derived. And basically the mineralogical and elemental character of the soil obviously mimics the rock from which it was weathered. In this particular example, let's discuss soil that contains, or rock, a parent rock that contains the element uranium. Okay, and uranium is a relatively common element in minerals such as zircon and uraninite that are present in some igneous and metamorphic rocks such as granite or gneiss. Those minerals are there already. The zircon mineral within those rocks contains trace quantities of uranium. Well, uranium is radioactive, meaning that over time it will experience a series of decay steps. It will produce a series of daughter products, ultimately leading to lead as the end product. Well, so in your diagram it shows uranium, it says 4.4 billion years. That's the half-life of uranium, meaning every 4.4 billion years, half of the parent product uranium will decay to the daughter products, and each of the daughter products have a specific half-life of their own. To focus on here, I wanted to look at this particular step in the decay process. Radon, which has a half-life of about 4 days, is one of the daughter products produced from the decay of uranium. Radon is a carcinogenic gas, and it can be hazardous to your health if it's allowed to accumulate in closed, poorly ventilated spaces, and then you breathe it. This picture is showing how a structure, house, building, right, business could be affected by radon. So here we have our bedrock, again, our gneiss or our granite that contains the uranium-bearing minerals. The uranium is decaying over time to form radon. Because the radon is a gas, it's doing its best to go from where it's formed in the bedrock through the soil and up to the atmosphere. Well, if the bedrock is fractured, if there's soil between the bedrock and the foundation of the structure, it's possible for the radon gas to seep into the structure through cracks in the foundation, right, drain pipes, whatever. But it gets into the foundation and into the poorly ventilated spaces of the building where it can accumulate and therefore cause the health hazard. So one potential way to fight this is if you know that the soil that you're building on is derived from rock that probably contains uranium-bearing minerals. One thing to do is to build your structure on top of basically what's called a depressurized zone, and control the entry of radon into the structure's foundation through that depressurized zone, and actually vent it out to the outside with a fan. So that's one way to mitigate radon. And just as an aside, I found this radon gas test kit at one of the home improvement stores, and I thought it was interesting because, I mean, for $10 you can buy this thing, take a sample of the air in your basement and send it in for analysis, which I thought was pretty cool. $25 lab analysis. Anyway, the back of this particular kit has some statistics that I thought was interesting. Again, this is from 2011, so it's a bit dated. But radon gas essentially is attributed to causing 22,000 deaths in the U.S. each year back in 2011, which outstrips drunk driving, falling down, drownings, and fires. So the presence of radon gas is not is important. It's not a trivial thing. All right, question number 2.
Please continue.
Thank you. Question number 2, radioactive decay of what element produces radon, the carcinogenic gas? That is D, uranium. All right, let's switch gears to another geologic hazard. Let's just talk about seismic activity in general. Geologic event or process powered by the energy released due to movement of the Earth's tectonic plates. We're talking about earthquakes. And seismic activity, damage from seismic activity could include surface displacement or rupture, right? We're talking about faults and tsunamis. Ground shaking, right, which would cause landslides, rock slides, seiches, or liquefaction. Again, we'll talk about a few of these in turn right now. So in order to fully understand the geologic hazard associated with seismic activity, I need you to time warp back to your 5th grade science class when plate tectonics was being discussed, and the fact that the Earth's surface is basically like a big cracked eggshell with the individual pieces of the shell moving around relative to each other, and some of those pieces are pulling apart, and some are pulling apart from each other, some are colliding with each other, and some are just rubbing past each other. Regardless, each of those plate boundaries, which are shown here on this map with the dark black lines, each of those plate boundaries is the site of different types and magnitudes of geologic activity, volcanic activity, earthquakes of various types and magnitudes, etc. On this map, just FYI, the individual plates of the Earth's lithosphere are color-coded, and they each have a name to them. And also the relative plate movements are denoted with the red arrows. So, for example, the west coast of the United States, well, the United States is all of North America, right? And Mexico, Canada, and the United States is part of the North American plate, and the western edge of it, just off the edge of California, is an active plate boundary. That's what gives California the big powerful earthquakes and the volcanic activity up in Washington State, for example, in Oregon. Note for those of you who are listening to me on the East Coast, and in particular New York State, right? We're over there someplace. We are not anywhere near a plate boundary, but that doesn't mean we still can't get seismic activity. But so just a mental note. We can take a look at seismic activity or the potential for seismic hazards on a nationwide scale in the contemporaneous United States. Again, the west coast of the United States is an active plate boundary, therefore seismic activity, seismic hazards, right, very high. The east coast, not on a plate boundary, so seismic hazards essentially low. And in the middle of the country, some places are just basically non-existent. So to head off the inevitable question that I know is coming, if the East Coast, for example, is not near a plate boundary, why do we still have seismic activity in that part of the country? And I guess the simple answer to that is just keep in mind that the continental crust on which we live is 4.5 billion years old, and it's old and it's ancient, and it's over the 4 billion years it's been tweaked and stressed and collided with other things and ripped apart in places. And so the crust in it, the crust in general has a lot of fractures and old faults already in it from past geologic history. Right now, the East Coast of the United States is not a plate boundary, right? But there are still deep through-going structures, faults, fractures that are remnants from, back in the day that once in a while will still move based on even stress that's tweaked onto the continent from the West Coast. So things move once in a while. The cracks are there, the faults are there, and they've been there for a long time. And once in a while you get movement along them, even in areas that aren't near active plate boundaries. So just keep in mind that the rocks break under brittle failure conditions, right? Conditions at the Earth's surface where the rocks are essentially cold. You apply stress to them and they break. When they break, that releases energy, and that's the earthquake. The Earth's surface itself is either displaced laterally or vertically, or both, when these rocks break, and the style of that displacement is governed by the type of stress acting on the rocks. So your stress types, your three basic stress types here, tensional stress where you're pulling them apart, compressional stress when you're pushing them together, or a shear stress where you're making them try to rub past each other. And when we're talking about displacement of the Earth's surface, we're literally talking anywhere from a millimeter or two up to kilometers, so the scale could be variable. So geologic hazards associated with the seismic activity could include surface rupture, where you have random small children being falling into large cracks and crevices formed in the Earth's surface. Other surface displacement on a very large scale is shown in this satellite image. This is part of this is a fault zone in China. Here's the fault. I'm outlining with my cursor, and the individual rock layers, which have been color coded for recognition purposes, you can see have clearly been split, and one side has been moved in a left lateral sense across the fault along the fault to the other half of that rock unit. So there's a scale bar down below that fault, or that displacement. Displacement along that fault is literally on the order of kilometers. Another example of surface displacement, okay, geologic hazard. This fault scarp, that's the actual fault surface itself. The fault is a three-dimensional planar feature, right? So this is the surface of the fault, and this half with the little shack on it has been down dropped relative to the other half, and this is typical of tensional stress, and would call this a normal fault. Closer examination of the fault scarp itself might show features on the rock that we call slicken sides, which are just highly polished surfaces of the rock that are formed when the rocks are moving against each other, and the fault surface itself is that smooth surface. It's just ground smooth by the movement of the rocks against each other. And slicken sides are good to see because you can see not only the fault itself, the actual fault surface, but also the sense of movement of the fault. All right, so how to mitigate seismic activity? Not much you can do to stop Mother Nature from creating an earthquake. You can't stop the Earth's plates from moving around, and they're going to happen. So, but the best thing you can do is just be prepared. First and foremost, think about where you are or where you're building relative to a plate boundary. Are you near an active plate boundary, right? Are you near a fault zone or a fault? Now, as I mentioned before, you might be in a part of the country where seismic activity is relatively low, but chances are pretty good you'll have faults in the bedrock close to where you are, and they may have not moved, or movement hasn't occurred on those faults for maybe millions of years or hundreds of millions of years, but that doesn't mean they can't still activate. Case in point, on your screen right now is a very generalized outline of New York State with the that's the Adirondack Park shown in that tan area. All the yellow lines that you see there are individual faults that have been mapped by geologists. So even though New York is not a real seismically active state, no plate boundary nearby, there are a lot of faults that have been there for a long time, and once in a while things move along them. The red zone is the Clarendon-Linden fault zone. A lot of the seismic activity in the state occurs along that zone of faults. Taking a closer look at the state of New York, color-coded for earthquake hazards. Again, the Clarendon-Linden fault zone is shown in the reddish area, and it's also interesting to note that the northern part of the state, near the St. Lawrence River, is also a relatively high seismic area, for the state, and it makes sense. I mean, the reason why the St. Lawrence River is there is probably because there's a fault there, and that's dictating the course of the river and the topography, and that would make sense. Another way to mitigate seismic activity would be as far as building stuff is concerned. And again, I'm not an engineer, but the general ideas are easy to see, I think, even from a geologist's perspective, right? The building codes exist in a particular area for a reason, and using the appropriate construction materials to build something would be wise. Maybe including motion resistant measures to a structure that you're building. Part of the reason why the death toll is so high in relatively undeveloped and third world countries, Iran, China, Turkey, Pakistan, whenever a big earthquake occurs there, and you have tens of thousands or hundreds of thousands of people die in a single earthquake, it's because there are no building codes, or very lax. You have high population density living in structures that are apt to collapse as soon as the ground starts to move, and the construction materials used probably weren't kept in mind, to withstand earthquakes very, very well. So you get a high death toll associated with that in certain areas. And as far as old construction goes, right, it's possible, I guess, to retrofit older buildings with motion resistant measures as well. Switching gears a bit here, still talking about seismic or geologic hazards associated with seismic activity. Let's talk about liquefaction for a minute. Liquefaction occurs in areas underlain by unconsolidated soil, water-saturated soil. Liquefaction occurs when the soil loses its cohesiveness when the ground starts shaking due to an earthquake. So the take-home message here is the soil does not turn to liquid. It just essentially behaves as a liquid as long as it's being shaken. The effects of liquefaction are fairly spectacular. Here's an example from the 2011 Christchurch, New Zealand earthquake. This car was on a seemingly solid road surface, and as soon as the earthquake sent energy through this area, the soils or the sediment on which the car was driving suddenly lost their cohesiveness and behaved more like a liquid, and the car sank into it. The ground shaking stopped, everything became like soil again, and there's the car half submerged. 2011 earthquake in Japan. Liquefaction caused these manhole, these pipes with the manholes on them to suddenly become buoyant in the shaken water saturated soil, and they just rose out of the ground. Back in Japan, 1964, Japan's on a plate boundary, by the way, so a lot of earthquake and volcanic activity in Japan. 1964, entire buildings just simply toppled over due to the earthquake shaking the ground, causing soil experience liquefaction, and the building just couldn't stand up anymore. Interesting to note that buildings remain relatively intact. They just fell over wholesale. How to mitigate liquefaction? Again, just be aware of the area in which you're building, and understand the potential for liquefaction in conjunction with the potential for seismic activity in an area. So again, proximity to a tectonic plate boundary, that's a big deal. Proximity to a existing fault, right? And how active is that fault? Also understanding the thickness of unconsolidated soil underneath your structure. The moisture content of the soil is good to know, and also the particle sizes of the soil. Sand tends to be affected by liquefaction more so than clay and gravel, but understanding what the soil is made of is certainly going to give you an idea of your liquefaction potential. I'm going to show you a real-world example of this, and my apologies in advance for the fuzziness of the picture here, but I'm showing you a block diagram of part of the Salt Lake Valley, just outside of Salt Lake City, Utah. So the Salt Lake Valley is a valley that trends north-south and is bounded on both sides, on the east and the west, by mountain ranges. And each mountain range is actually the foot of each mountain range is actually a fault, right? That separates the mountains, which are being raised up relative to the valley, which is being downdropped. In the Salt Lake Valley itself, geologists have actually mapped faults not only in the mountains, in the rock outcrop itself, but also out in the valley fill and the valley floor. And each of these faults have names, and in the block diagram here, their projection at depth, where they go and how they coalesce at depth, is noted here. What's interesting about this diagram is that geologists think that the center of the Salt Lake Valley is underlain by soil that might be 3,000 feet thick, maybe close to a mile thick in places. So this thick sequence of unconsolidated wet sediment, right, with subsurface water, is just absolutely ripe for liquefaction to really raise to really do some damage out there. And if we took a look at that block diagram in kind of a cartoon map view, again, here's the Salt Lake Valley. We're just looking at this. Here are the mountains to the east and to the west. The red area of the Salt Lake Valley denotes an area of very high liquefaction potential, essentially, right? If a magnitude 7.0 earthquake occurred along the fault line in that area. What's interesting to note is that even though the earthquake itself might originate in the fault that's in the foothill of the mountains, notice that the ground right next to the mountain has a very low liquefaction potential. It's out further away in the valley where the sediment thickness, the loose sediment pile is thicker. They'll get hit hardest by the liquefaction phenomena, even though these folks where the cursor are physically located closer to the origin of the earthquake. So interesting to note. So how to mitigate liquefaction? Again, just try to identify the potential for it and understand that it could be an issue where you live. On a very local scale, you might treat or prepare the soil, compact it down, mix the soil with cement, maybe some grout to try to take away some of its loose cohesiveness. But again, not much you can do on a large scale with this. Question number 3, please.
Chris.
All right, thanks, Howard. Question number 3, liquefaction is most pronounced in areas underlain by loose, unconsolidated soil. Okay, to address the earlier question about karst and what is karst, here's the description of karst. Again, it's a type of topography that forms via the dissolution of soluble rocks in water. The rock types that are susceptible to karst or karstification include limestone and marble, which are both comprised of calcium carbonate, dolomite, which is also calcium carbonate but with some magnesium in there as well, rock salt, and ATL, and gypsum, which is a hydrated calcium sulfate. These rock types are susceptible to karstification. Now, as far as rock salt and gypsum are concerned, those two rock types, so first of all 4 of those rock types are sedimentary rocks, except for marble. That's the metamorphic equivalent of limestone. Rock salt and gypsum formed through the precipitation of salt or gypsum when the water evaporates, right? So salty water evaporates and the rock salt and the gypsum precipitate out. If you add water back to them, they'll dissolve back into the water. Limestone, marble, and dolomite are a little bit different. It's not the water itself that will dissolve the rocks. It's the carbonic acid inside the water. It's what dissolves those rock types. So carbonic acid naturally forms in water when water and CO2 combine, gives you H2CO3. That's carbonic acid. And it's the carbonic acid that will actively dissolve limestone, marble, or dolomite. Now, carbonic acid is, again, it's naturally occurring. That's why rainwater is slightly acidic because of in part because of the carbonic acid content within it. But obviously, the more CO2 that's in that you have in the atmosphere, the more carbonic acid you're going to have in the water, and the more dissolving power the water will have, right? That's why in areas like, well, in very urbanized areas, New York City, for example, you can see building facades that used to have, made out of marble or limestone, that used to have, like gargoyle statues, or you go to a cemetery and you see a marble or limestone headstone that you can't read the words on it anymore. They've all been dissolved off. The gargoyle's been dissolved, out of its shape. It's because the carbonic acid in the water and all the CO2 in the atmosphere mixing with the water has started to dissolve those things away. Regardless of the mechanism, the features that result from karstification include sinkholes, caves, disappearing streams. In other words, streams that flow along the Earth's surface and then just kind of disappear into the ground. You can't really see where they go from there. Underground rivers, etc. In other words, the dissolution of solid rock creates cavities, open spaces, caves, right? Pathways for water to move and flow. And the more water that moves through those open spaces, the more those open spaces will be dissolved away into bigger and bigger open spaces, because you're introducing more water with more carbonic acid in it. So it's just a self-perpetuating thing here. Karst features typically make the news because they give us relatively spectacular things to look at. This is a sinkhole, right? So in other words, this house was built on top of limestone, maybe, right? Where the limestone was being dissolved away through karst, through a karst process, and the cavity underground became so big, the overlying soil couldn't, and house couldn't be held up anymore, and the whole thing just slumped into the hole. How to mitigate karst? Again, identifying the potential for karst via consulting geologic maps, hiring a geologist to do geologic reconnaissance, etc., is the best way to go. You can consult you can consult maps, both on a nationwide scale and more local scales, to see where limestone is, where dolomite is, where marble is, and you get an idea of, if those rock types are there, then karst features will be present. The extent to which karstification happens obviously is largely dependent on the amount of water. So you can have limestone in the Mojave Desert that will experience karstification at a very slow rate, just because there isn't a whole lot of precipitation there, a lot of water to mix with or to interact with the rocks. However, that same limestone outcrop in a more humid climate, more temperate climate, where you have a lot more rain, water will dissolve away faster. Statewide maps exist showing, in this case, New York State, showing the distribution of limestone. We know limestone is susceptible to karstification or to karst, and so if you're building something near where limestone is present, you might want to keep that in mind. And again, how to mitigate karst, you really can't. Some people try to dump fill material into sinkholes to try to plug up the hole, and that might stop it on a very short time scale, but it's just a small band-aid on the overall problem, and you can't really do much about Mother Nature dissolving rock with water. So again, just being aware of the situation is worth a lot. Question number 4, please.
Chris, please continue.
Thank you. Question number 4, which acid is formed from water and carbon dioxide that creates karst topography in limestone, marble, and dolomite? That's C, carbonic acid. All right, the last little bit of the presentation here is just a very topical discussion about how certain rocks or rock types can create geological hazards. So first, keep in mind that the physical characteristics of rocks are due to 2 factors: their mineralogical composition and how they formed, right? And as you know, there are 3 flavors of rocks, right? You have sedimentary rocks, rocks that are created by loose sediment being lithified into a solid rock; igneous rocks, which are formed from magma or lava that have cooled and crystallized; and metamorphic rocks, which are formed when pre-existing rocks are subjected to heat and/or pressure. The result is that some of these rocks can possess characteristics that can be geologic hazards. So let's talk about sedimentary rocks for a minute. And in particular, I just want to briefly discuss bedding planes and interbeds in sedimentary rocks. The picture that I'm showing here is an outcrop in a road cut, but pay attention to 2 things. First of all, notice that some of these layers of rock stand out more. They have a better profile, right, than others. What this is telling us is that some of these layers of rock here are more resistant to weathering, right? So they weather away more slowly and therefore develop a stronger side profile, whereas intervals like this are weathered away more easily and therefore erode away more quickly relative to the others. So when we talk about bedding planes, we're literally talking about the physical line that separates one layer of rock from the next. Holding a rock in your hand, it's easy to see bedding planes. Here, it's easy to see them in in the picture. Sometimes, by definition, a bedding plane is relatively a relatively weaker surface than the solid rock on either side of it. Okay. In this case, in this case, the bedding plane is really pronounced because you have a rock type that's probably shale, right? That's highly susceptible to weathering versus a siltstone or a sandstone, which isn't. So that bedding plane is becoming more and more of a deciding factor in this hillside falling apart because it's a really obvious blatant weak spot. Interbeds refer to a layer of rock amongst other layers of rock of a different type. So again, using this picture as a tool to illustrate this, we can think of the shale as maybe interbeds between the sandstone layers, right? And again, clearly the shale is the weaker of the two units, and if any failure was going to occur on this outcrop, it would be either the contact between the shale and the siltstone or the actual shale itself. Now, as long as those sedimentary rock layers are horizontal, things are relatively, well, about as stable as they can be. If you tilt them, if Mother Nature tilts them, then of course we're creating again the bedding planes and the interbeds that are the weak points before are even more so now, because now we have the ability to introduce water, melting snow or rain, whatever, into the top of the outcrop, which will then preferentially flow either along the bedding planes or through the weaker interbeds, and of course the water will act as a lubricant, allowing movement to more easily occur if one of these layers wants to separate from the other one. And also by you know that the tilted rock unit, the face of the tilted rock unit is called the dip slope, and that's something to note. It's the idea of weak points within rocks is not just a sedimentary feature. We can see that in some metamorphic rocks. In this case, metamorphic rocks that are foliated. And the foliated metamorphic rocks, slate, phyllite, schist, and gneiss. Although I'm going to leave gneiss out of the discussion here because gneiss is actually banded versus it's past foliated and just banded, right? But slate, phyllite, and schist are the three that are more susceptible to maybe failure along the foliation. So this is now a crop of schist, and you can easily see this outcrop. This outcrop has what I'm going to call layers, quote unquote. These aren't layers of sediment. These are layers formed in the rock by heat and directed pressure. And if we take a look at a piece of that schist more closely, we can see that again, those aren't bedding planes. That's foliation that we see, and the foliation is denoted with elongated micas. We have that are all oriented in the same way. And if we took a look at this under the microscope, again, we can see that the mineral grains that make up this rock are all flat and elongated because of how this rock was formed, and the flat and elongated nature of those, in this case, the mica minerals especially, give the rock the foliation. And the weak point in this rock, again, is one plane of foliation to the next. So just to wrap up, we can think of this idea again, very generalized sense. If we have a structure built on an outcrop of, in this case, sedimentary rocks with shale interbeds, and we know that shale is kind of is rock type that's easily that fails more easily than say siltstone or sandstone, right? If the shale beds are tilted, we might experience slump across or along the shale interbed. in this diagram as well. If extra load is placed on top, that might force slippage along the shale interbed. And also, if we introduce water into these rocks, again, the water will act as lubricant, which might initiate or help initiate slope failure. And one way to get around this, again, one possibility is to insert some pipes to maybe drain the water and help relieve the pressure to keep that from falling. We can play the same game with bedding planes or foliation, the metamorphic rocks. Again, these lines would represent foliation, and the same potential problems could occur there. All right, question number 5, please.
Please continue.
Thanks, Howard. Question 5, which of the following rock types possesses foliation? It's the metamorphic variety. That concludes today's webinar. I did want to put a shameless plug in for the upcoming webinar that ATL is offering. It's the second half of the one you just saw, so Geologic Hazards Part 2. I will be giving this webinar next Wednesday, November the 11th at 2:00 p.m. So I invite everybody to join me for that webinar as well. If you have the original email that allowed you to register for this one, you could also register for Geologic Hazards Part 2. If you don't have that anymore or didn't get that in the first place, please contact Zach Short, zshort at atlantictesting.com. Email him and he will get you the necessary information to register for that webinar. Again, that's next Wednesday at 2 p.m. So with that, I want to thank you all for joining. And Howard, are there any questions or comments?
If there are any other questions or comments you would like to share, please provide them now. Chris, there are no further questions.
Fantastic. Thank you, everybody, for your time. I appreciate you joining me today. And again, I hope to see you next Wednesday. Thank you all very much. Take care.